Today I thought I'd do a quick tutorial just kind of showing the concept of making grass move using VelcroPhysics, the new name for the Farseer engine. So first thing I'll do is start by making a new project, and it could be a monogame, it could be Windows. If you want to do Linux, you can go with cross-platform. That'll work on Windows or Linux. We're going to go cross-platform. And I'm just going to call this grass demo, just a demonstration of grass using VelcroPhysics. Alright, so the first thing you'll need to do is download the VelcroPhysics engine if you haven't already done that, formerly known as Farseer. You can do a Google search for that. And you'll just need to navigate to the monogame project that's in there and compile it. Another thing you can do if you want is you can just add solution in your grass demo, if that's what you're calling it. Go add project, add existing project. Then you would navigate to VelcroPhysics and then just look for the monogame project right here. And you would open it, and then you'll see it here, over here in your Solution Explorer, and you can build it, and you'll need to reference the DLL once it's built in here. So once the DLL is built, you can actually just delete this from your solution. You don't have to have it in here anymore. So we'll just remove it. So click on remove, and it's already built, so we're not worried about it. We just need a reference to the dynamic linkable library. Go add reference, and it may show it here and you can check it, but that might not work. So what I would actually do is browse to the DLL. I mean, that should work, but it may not. So browse to the DLL for it, the monogame DLL, and click add and click OK, and then you should see it pop up in your references. So now you have access to VelcroPhysics in your game one. We'll start by clearing out some of this stuff and just prep things like normal. So once you've kind of erased a bunch of this extra stuff, actually first let's go over to solution and we'll add a folder. Add folder. I'm going to call this hide. So this is just going to be used to hide stuff that we don't really need to see at the moment, such as our icon. Yeah, most of this default stuff we can hide in here. And minimize it, and then all we're seeing here is the game one. So we'll have to close bracket that. I added this rectangle, grass 1, grass 2, grass 3, for the 3 grass images and 1 for big grass. I think for now though, I'm probably just going to use the big grass image as a platform and just draw lines using this pixel. I'll just stretch out the pixel to make lines, and we'll use those lines to represent where the grass is. And the texture 2D is going to be the sprite sheet that will contain the necessary textures to compose any kinds of grass that we want to use. So first thing we'll do is double click on content, and then we can add an existing item. It'll make a copy of that into this directory here. And after you've added that, you may want to add a font. In this demo, I'm not going to add a font right now. So this is what it looks like. All this white is actually transparent pixels. It's just that we got a white background. But these will be the grass bits. There will be 3 different types of grass that can go over top of this in layers. And I would break this up into 3 quads, and each quad will move a little bit differently. And if the player or something hits the grass, it'll actually interact with those quads and cause the grass to swish this way and that way. Okay, so this will be our big grass that we'll use for a platform. I think in this demo, I'm not going to show creating the quads and building them around the lines. We'll just start with making the lines flex and move based on any interactions with the object that's going to be used to represent where the player is. Just make sure to save and hit build. Okay, so I made a constructor, and I'm just going to use a lot of hard-coded values in this tutorial. We're just setting the screen resolution here. For now, we're not using the depth buffer. Setting high def, that's not really important. You don't have to do that if you don't want to. Now, in initialize, we're going to set sprite batch in there, and a pixel. Okay, so if I zoom in on this image here, I have this information window open here so I can see what coordinates we're dealing with. For the first image, we can start at the top left-hand corner and go to the right. Well, you can look at the W and the H on the right-hand side to see what kind of coordinates you want. Same sort of thing for the rectangles for these pieces, or the image sources for those. But if you want to divide them into 3 parts, you just go a third down the height of the rectangle when you're making your UV coordinates, if you're going to set up 3 quads. I wouldn't use rotated regular sprites for that. I would actually use vertices or a quad class that works the same as sprite batch, and then that way you can distort your grass the way you need to. So if I add this green layer to the background temporarily, you can see up in this right hand corner here at coordinate 382, 0, width 2, height 2, I have this white pixel here. We're going to use that as a texture source, UV coordinates, to have the graphics card stretch out and make into a line at whatever angle we need it. So let's just disable that green layer. So the pixel that I showed was at 382, 0, one wide, one high. And these are the coordinates of those three little pieces of grass. I may end up using that later. For this tutorial, we're not going to use those probably. So you don't really need those necessarily. The platform for the big grass, 380 wide, 122 high. So adding our load content, we've got to load in the texture that contains all our little bits of grass and that little pixel using content.load. Okay, and so we'll add this update. I got this one here, which, I mean, normally we'd have that up here, right here. But I think this might be temporary, so I'm just putting it before update, and we'll get the player chords. For now, pretend that the player chords are at the mouse position. And so the screen position will represent the actual position on the screen for any given item that we need to look at. For now, we're just going to draw the background as color transparent black. If you have a full background to add, then you don't need this clear. You can just draw it inside the begin. And then I'm drawing the big grass at 300, 600 minus 20. I'm subtracting 20 from the 600 coordinate. I could just write 580 in there, but I'm subtracting 20 because I want to offset it up from where the actual collision box is going to be, because the top parts of the grass in that image are stuff that your player's feet should be able to sink into. Now, if you go back up to the top, I added this world, and what that does is it's basically dispatched to take care of all the collision detection, all the collision responses in the entire world. So that's actually what processes it, and it's going to process it based on some gravity value that we give it when we initialize it. Now we're going to have to go quick actions refactorings here and tell it to use using VelcroPhysics dynamics. So now we got this using up here. We'll have to do that also for the fixed mouse joint. And now we got the joints, and so we have access to that. And what the mouse joint will do is it'll attach a little rectangle body to the mouse position in each frame. So as we update the frame, when we move the mouse around, it's going to change the attachment point and it's going to drag it along with it. So that's just for temporary purposes. So next we'll add a collider body, assuming that the hero body is at the mouse joint position for testing. I mean, you could even call this hero body if you wanted to. I'm going to just refer to it as collider body so we know that that's the item we're moving around that's colliding with things. Each body can have mass and different properties and such, friction and that, and the joint just determines what it's attached to. Okay, so we'll go down into initialize and we'll start setting up the mouse joint in the collider body and the world. First thing we'll start with is world. Okay, so right here we need to add the direction of gravity. And I'm just going to go 0 because there's no horizontal wind effect. And so we can go new vector 2. And I'm going to use 9.8 meters per second as the acceleration downward. I'm going to right click on body factory and we're going to use VelcroPhysics factories. I decided to use this con instead of convert, but we'll have to set up some usings for that. So go up to the top and we'll put in using VelcroPhysics.utilities. And that should give us our converter. Then we can say using, because normally you have to type in a bunch of stuff. Like normally I'd have to type in convert units to sim units, and I don't want to type out as much, so I'm just going to type in con. And then up here, we can say using con is equal to convert units. And it's going to be Velcro utilities convert units. So I'm just right clicking on that to get it to that. So for categories, I'm just going to right click this using VelcroPhysics collision filtering. Alright, so once you got the world set up, that's going to simulate our world based on the gravity you give it. The first collider body we're going to make, we're going to use the body factory to make it. I'm going to create a circle. You get a bunch of different ones in here. Like you can make a capsule, ellipse, rectangle. I'm going to go circle. We've got a pass in the world. You see here we can add a radius and a density. I'm just leaving density at 1. Radius is going to be 8 pixels, so I'm converting the display units to sim units. Okay, and I'm going to set the position, and again I have to convert to sim units, and pixels it's at 410. Doesn't really matter where you start out your coordinate, it's going to attach to the mouse right away. Body type is dynamic, meaning it moves. I'm going to give it a mass of 0.4, so 40%, 20% restitution, 40% friction. So restitution is bounciness. Friction is how strongly it grips a surface or sticks to something. I'm making this a category 1 for what kind of category this falls into, and you can just pick a category for each item. This one I'm setting as category 1, and I'm saying it's going to be able to collide with anything in the world. So anything that has a body attached to it that can accept collisions, this will be able to collide with any of those, no restrictions. And that would be the player character, so I probably wouldn't have any restrictions on that. I set fixed rotation to false, just for fun. I mean, you could set it to true. Your body's not going to rotate at all. If you do that, it doesn't really matter. I'm setting it to false just because I thought it would be kind of neat to watch it rotate. We'll add the rotation feature. And so if your character collides with anything, you can actually take advantage of that rotation feature to make them roll in circles or something like that, depending on what it is. So here we're going to attach the collider body, which is what we made here, to our mouse using the joint factory to create what we call a fixed mouse joint. So we tell it that the collider body is always going to be attached to this mouse joint. And we're just going to adjust the mouse joint to be at the position of the mouse. And I just set max force to 500. Depending on what you do, you might want to change that. I don't know. Okay, so in update, let's go to where we get the player coordinates. We'll set the joint position for the mouse fixed joint, to be at where the mouse is. Using this mouse joint, I'm setting world anchor B to be at the mouse coordinates. So I'm just converting the display coordinates here to the sim coordinates. And I just put a note here that if you had a locked frame rate, 60 frames per second, if you wanted to, you could just enter a number that represents that frame rate. Or you could do this. We're going to use system here so we can use math, and pick whatever is less. The elapsed game time, total milliseconds, times 0.001, or if 1 divided by 30 is less. So 1/30th would probably be the slowest we'd ever want it to update. But I mean, if this is less time, then it'll do a calculation update, a step update in the physics. So I'm using this screen pose here. I got it outside of this so that I can use it in update and in draw. And I don't have to pass it or anything. So I'm setting screen pose to be, I take the sim coordinate of the collider body, and the collider body's position would have been updated based on this mouse joint world anchor B, which is now set at the mouse position. The collider body's rotation could also be updated depending on whether it collided with anything. So I'll set the screen position to be equal to that body converted to display units. I mean, technically we could probably just say screen position is equal to the coordinates of the mouse, but I'm also doing this. If the screen position Y, and you don't necessarily have to do this, but this is based on the horizontal vertical values of the resolution. I'm just saying if it goes outside of the screen boundaries, I'm just setting it to the other border or whatever. If this wasn't attached to the mouse, then if it fell off the bottom, it would fall back off the top. And if it went off the right side, it would appear on the left side. So that's all that's doing. It's just kind of a demonstration that you can directly set the transform for the collider body position, and you can set the X or the Y or both. We'll go down into draw. Okay, so I added this line here, and we're going to draw at the screen position, that white little pixel. But what we're going to do is we're going to scale it right here to 9.6 times wider, 9.6 times taller. It just looked like a good size for it. And it is kind of based on the dimensions of the body that we gave it, which I believe was a radius of 8, something like that. Yeah, right here, 8. So you can play around with these two numbers and that radius number until you got something that kind of reflects what you need. Here I'm saying origin is 0.5, so that's halfway into the rectangle, which is 1 in width. So it's going to rotate around the center of that rectangle. And I'm coloring it red, and I'm using the collider body's rotation. So if it does actually collide with anything, it can start rotating too, depending on how it hits it. So we'll test out what we got so far. We don't have anything to collide with, but we should see a red rectangle attached to the mouse. Okay, so I got a system value cannot be null. That would mean that our texture is null, didn't load. So let's see if this matches up with whatever we got in here. Oh, I just realized something. Make sure you don't forget the base dot initialize, which is maybe why it's a good idea sometimes not to delete the defaults and just delete what you need to out of them. If you run the code, you'll see that you got this red little square that follows around. It has a hidden circle body that is used for collision, but right now we don't have a body set up for the platform. So we'll add that next. Under collider body, we'll add another body called big grass body. And that will be the collider for the grass, that big platform. Going into initialize again. Under our mouse joint, let's add stuff for the platform collision body. So I added this big grass body is equal to bodyFactory.createRectangle, and we're giving it the width, and I'm going to give it 88% of the rectangle width for that element on the sprite sheet, the big grass.width. So 88% wide, and I'm going to go 6% high because a lot of it's just fluff that's sticking out that you're not actually going to collide with. Density of 1 as usual, and I'm going to set the position, and in this case I'm just hard coding the position in. I'm not using variables. Normally you'd use variables for this stuff because you'd have platforms all over the place and you want to sort of reuse the same type of code. So just for this example though, we're going to do it this way. So I'm going 300 plus the width of the grass platform divided by 2, subtracting 10 just because I noticed that it should be approximately 10 less than the calculated position of the center based on where it looks like it should collide on the sides. So I adjusted it by -10. You don't have to do that. Normally you just have it like that, but I'm just going to say -10 so that it looks a little bit better when it collides. As far as the height goes though, because of adjusting where it actually draws it, we're already subtracting in a certain amount. So I'm just going with positioning it in the center of that piece of grass based on where we're going to put it. So just remember the body position of anything you have, that position is the center of that item. Body type is static, it doesn't move. It's got a 0.2 bounciness to it. Mass didn't really matter, I gave it full mass amount 1.0. Friction of 0.8, so things will tend to cling to it. I put it in category 2, and it only collides with category 1, and so this grass is only going to respond to this hero type character. I could create other types of moving characters too, and I could put them all in the same category, and then any of those categories, if they're all category 1, then any of those creatures would affect the grass and make it move. Here I'm just practicing my Japanese, and I inserted this little reminder image of what this is for. So now that we've created this big grass body, when this world.step is processed, it's going to take care of that part of the collision detection and response for us and update the mouse joint position accordingly, as well as the rotation amount. So there should be some rotation when it collides, and we should see that now when we try it. So now when I bring this mouse down to the platform, drag it along it, you can see that this will roll as it collides because there's quite a bit of friction there. Now, for simulating the grass, instead of using a distortable quad, I'm just going to draw a line representing where that portion of the grass exists. Okay, so I added this draw line here using a start and end point, color, default thickness value, and what it does is it gets the end point and the start point and calculates a rotation amount based on that, using opposite over adjacent. Using the texture and the starting point, it will use the length of this calculated segment as a scale amount in the horizontal direction. So it'll first scale it from wherever it starts at along the horizontal direction, then it'll rotate it by the amount calculated around this origin. This would be the left center point on the pixel. This assumes the pixel is 1 wide and 1 high. If it's not, it'll screw up this scaling calculation. So just to be safe, you could actually have this, where you say if the width is greater than 0, then you just correct it. So I think to be safe, we'll just leave it like that. And now we should be able to just say draw a line here, and we can draw a line representing the grass. But first, we'll have to create a body to simulate what the grass is doing. Let's go up to the top. Alright, so we'll add in this grass body, grassbod1, and a joint, which is what it's going to be attached to. The weld joints aren't necessarily fixed, they can be rotated when collided into. Alright, and we got grass body 2, which we're going to use for a second piece of the grass to show how you could create a chain of grass pieces. So in this chain, we're just going to have body 1 and body 2. because this is just for demonstration purposes. Moving down into initialize, under this big grass initialization, I added this dynamic grass for the bottom part, which will be grass pod 1, and I made it a rectangle using half the width and 40% of the height. So we could actually probably even go less than 40% if we're going to make it into 3 segments. For now I'm just going to use 2 segments, so I'll just say 40%, density 1. I'm setting the position to be horizontal position and 600 minus half the height of this segment. So it's a 40% segment, so half of that I'm going to set it at 20%. So in the middle of the rectangle that we want to simulate, and this rectangle is only 40% of the height of the piece of grass in the image. So we just want the bottom. Now I'm setting it as dynamic. I just picked some values for mass, restitution or bounciness, and friction. This grass is going to ignore gravity. The WeldJoint will slow it down over time. And I'm setting it as a category 3 type. I'm allowing it to collide with category 1, and category 1 is the hero character. Or it could be any dynamic character that we set as category 1, or whatever category you're using. Okay, since grass body's collision category 2, the grass can actually move through the body and it won't be affected by it, which is kind of what I want. And for the joint for the grass, that's where we're welding it onto, creating a weld joint. And body 1 is the big grass body, that's the platform. Body 2 that we're using is the one we just made, which is that bottom piece of grass, which is what we're going to weld onto this. And I just set the points for it to be 360 and 600. It's hard coded. One is for the big grass body, one's for grass pod 1. So this is where it's welded onto. I set collide connected to be false, so we're not going to collide with connected pieces. I think that's what that means. And I got this set to 17 Hertz. I think that's for how often it updates the calculation for this. I think typically it would be 30. I'm putting it at 17. If you set this higher, it's going to be more rigid. If you set this lower, it won't slow down as fast, so it's going to be a lot more springy. And your dampening setting will actually determine how much dampening there is on the springiness, sort of the springing effect of this joint. So you can actually adjust either of these to kind of affect how springy this joint is going to be, or how bouncy it will be. We could actually copy this and make a bod 2, but I think for now we're just going to work on bod 1, joint 1. Alright, so let's go down to draw, and we'll draw that segment of grass. So the first thing you'll notice is I added this grass vector, and I'm converting to display units the body 1 position, which is the center position, or the resulting center position of the grass. So if something collided into it, it's going to move that around. Since it's welded to the platform, it's going to pivot around that weld joint, and we can get the center position of the grass after the world calculation. We need to subtract the 360, 600 to get the vector of the grass. So that's basically putting this at the origin. So we just have the grass as a line segment at 0, 0 and rotating around. Times by 2 because the line is only going to the position of the grass, which is the center. We need to times it by 2 so we get the full length of the grass. Then what we do is we calculate the real position as being, and we could do this in either order. Actually probably make more sense if I said it's at the starting point of the platform plus the vector for the grass. So now we've offset that vector so it's visually attached at the end of the platform, or on a point on the platform, which is actually where that body is. So we've kind of done the reverse of this. It's just we had to have this times 2 to get the actual vector. Then we draw the line from where it starts to that real position, which is this grass vector added to this. So again, these are hard-coded values. We normally want to make these into variables. And there are several ways of optimizing this too. Just going to color it green and give it a thickness of 2. In fact, since its default is 2, we can actually just do this. So let's start. So now we can actually collide with it and it'll kind of spring back. And if we don't really want it to have a springy effect, we can change some of these values up here too. I think if I change this to 30, it would be a lot more rigid. If I change dampening from, say, 0.23 to like 4.23, we'll probably lose all our springiness. If we can push it, it'll just straighten out. Okay, now let's make the second part. So we'll copy this and then just modify the values. Alright, so I copied it, changed these all to 2s instead of 1s. Looks like I accidentally forgot to change this one to 2, even though it's the same values. And what you'll notice that's different here is I'm setting this to be at a position of grass height minus grass height times 0.6. So we've already went up 0.2 to get to the center of the first one, that would be the position, and it's actually 0.4 up in height, so that offsets 0.4 or 40% of the height up. And we want to go to the middle, so instead of going another 0.4 up, we're going to go 0.2 and add those two together, that's 0.6. So the height times 0.6 gives us the center of the second piece of grass. So everything here is the same. Yeah, everything else is the same. It's category 3, Clydes of Cat 1, which is our characters. This time, for the joint that we're making, we're attaching to GrassBod 1 from GrassBod 2. And I'm not actually sure if it matters, but I just have the one anchor point that I really want to use, so I'm anchoring it on GrassBod 1 at 600 minus 40% of the height, which is the end of the piece of grass. So that's the initial joint position that it's welded to. So when it moves around, it's still going to be welded to that position regardless of where it moves. So if it moves down and to the right, it's going to be welded to that endpoint that it moved to, rather than where it started. Or let's go down to draw, and we'll add in the number 2 grass vector. Just going to move this all up. So this will be the number 2 grass vector. Okay, so now down in draw, we're going to add this grass vector that we made here. And to get that, we'll calculate in display units the new position of GrassBod 2. And again, we have to times it by 2, but first we have to subtract it from the end point of the last piece of grass so that we get the actual vector. Multiply it by 2, so that's instead of going from the tip to the middle, it's going from the tip to the other tip. And then we say real post 2 is equal to the end point of the last piece of grass, which is right here, and we add in this new vector that we calculated for the second piece of grass. So it's coming off of that end tip. Then we draw from the first piece of grass's tip to the second piece of grass's tip. Hopefully that works. Let's try it out. Okay, that's tip 1 there, tip 2 there. So now I'll do some pretty realistic simulation with a piece of grass. Keep in mind the rectangle is actually bigger than the line segment we're using. The line segment's just a representation. We're going to have an actual image in here that will be wider than what's shown in this demonstration. And then it'll look a lot more natural. And what I would do is I would add a third piece so we get the full length of the grass. And instead of doing 40%, because we're already at 80% here, I would do like 33.3, so it's in thirds. So 0.333 times the height for each line segment, and then you'd have it divided up into 3. But what we'd also need to do is make this into a class. We'd want to have a grass piece class, and instead of making like GrassBod 1, GrassBod 2, joint 1, grass joint 2, grass joint 3, we'd have a grass class and then a grass manager that would manage those arrays of grass. What you could even do too is you could have pieces of grass surrounding certain key blades of grass that would just approximate the motions of the surrounding physics calculated grass. So that way you're not making all kinds of calculations for a whole bunch of grass, just key portions of grass which will sort of puppeteer the other pieces in between. And since I don't have a lot of time, it's not that difficult, but right now I can't really go into showing exactly how to set up all the quads and how to create classes for managing the grass. But hopefully this will give you some idea of how to do that. Thanks for watching.